Okay, so last time we began our discussion of different notions of convergence of a series of functions or a sequence of functions. And so on the screen, I've reviewed the three major types of convergence we'll be working with, in particular in the context of Fourier series. And so remember, we're considering the problem where, okay, let's suppose I have some sequence of functions f sub n of x, right? For each little n, I have a different function. And we look at the sum from n equals 1 to capital N of these functions. So we get a series of functions, for example, a Fourier series or a Taylor series or something like that. And so the problem is, well, what do we mean to say that this function or this series converges as n goes to infinity to the function, our given function f of x, right? And so this is a special case of a more general problem, which is, well, instead of this particular type of function where I'm adding up some list from a sequence, I could just consider any particular sequence of functions that depend on capital N and think about, well, what do I mean when I say that this sequence of functions converges to the function f, right? And so this question is relevant for us because we're going to consider the problem of when and how a Fourier series will converge to a given function, right? And so, right, so the three different types of convergence, just as a quick review, the first type is probably the most natural or familiar to you, which is just the notion of pointwise convergence. And so, well, pointwise convergence, we say that the series will converge pointwise if I look at the difference of the two functions, right? I have my series here and my function here. I take the absolute value of the difference and the difference converges to 0 as n goes to infinity for each point. Right, so as long as you fix your point x, this difference is just some number. And we require for pointwise convergence that for each such x, if I look at this difference and let n go to infinity, the difference converges to 0. And in this case, we would say that the series converges pointwise to the function f. Right, and so the kind of distinguishing feature of this type of convergence is that your rate of convergence is allowed to depend on the point. Right, so for example, there could be some points where the convergence is very fast, and there could be some points where the convergence takes more time, right? And so, well, for some applications, you don't want that to occur. And so we introduced this other notion of convergence, which is known as uniform convergence, say on a particular interval between A and B, a particular closed and bounded interval. And uniform convergence eliminates this possibility that the rate could depend on x. So for uniform convergence, we want the rate that the series is converging to the function to be uniform over all points, which is where the word comes from. And so the way to do this precisely is, well, I still look at the difference of my series and my function, but I take the maximum of this difference over the whole domain, and I require that the largest possible value of the difference between these two things converges to 0 as n goes to infinity, right? And so in particular, well, if the largest value possible difference is converging to 0, that means that for every point in the interval, this difference will converge to 0 as n goes to infinity at a rate that's no slower than at the largest displacement, or the point where it's the largest, right? And so this convergence is stronger than pointwise convergence, right? Uniform convergence will necessarily imply pointwise convergence because we have a stronger condition here. Right, and so if this condition is satisfied, we say instead that the series converges uniformly on the interval between A and B. Right, and so then there was a third notion of convergence, which may be the newest to you, which is typically called mean square or L2 convergence. Mean square is because, I mean, this is common notation in statistics, for example, or sorry, common terminology in statistics, and this type of convergence shows up a lot in that context. And so now this is not a pointwise notion of convergence, but rather an integral notion of convergence. And so if we have our series of functions here and our given function f of x, remember we say that the series will converge in the mean square or the L2 sense on our fixed interval, say between A and B. If I look at, again, the difference of the two objects, but now I square it and I integrate the square between A and B, and I require that this whole integral converges to 0 as n goes to infinity. So this is like not a pointwise definition because you're taking into account at once all the values between A and B, in an integral sense, and you want the integral of the difference to go to 0 as n goes to infinity. And so if this happens, we say that the series converges in L2 on this domain, or in the mean square sense. Right, and so I've reviewed all these concepts for series from n equals 1 to capital N. Everything here works for more generally for just sequences of functions. If you just replace the series here by like gn, right? So I could have instead I could have like a gn of x here, a gn of x, gn of x. And in each respective case, we would say, oh, well, the sequence gn converges to f pointwise if this occurs, etc. Okay, and so we ended the lecture last time with an example, which was of this form, right? So we were looking at a function gn of x, which is defined to be 1, right? For each capital N, which is an integer, we let this function be 1 if x is between 1 over n squared and 1 over n, and 0 otherwise. And so we're considering the domain between 0 and 1. Right, so for example, maybe n is pretty large, so this is 1 over n squared, and this is 1 over n. Right, and so in this region, the function is equal to 1, and everywhere else it's equal to 0. Right, so over here it's equal to 0. Right, and so we saw last time that this is an example of a function that converges to 0 pointwise. So here my function f of x, if you compare to the examples from above, is the function that's equal to 0 for all x. And so this is a sequence that converges pointwise to 0, basically just because if I fix any point x, eventually this interval between 1 over n squared and 1 over n will not include the point x. And so the function is equal to 0. However, no matter what your value of n is, there's always some point x which is in this interval, right? So this interval between 1 over n squared and 1 over n is shrinking in width and moving towards the origin. But for any given n, there's always some points that are inside it, no matter how small it is. And so the maximum of this function is always 1. And so we concluded from that that this can't converge to 0 uniformly, right? Because there's always some points where it's very far away from being 0, no matter how large n is, meaning in the limit. So this shows that uniform convergence is strictly stronger than pointwise convergence, meaning there are sequences of functions which converge pointwise, but which do not converge uniformly, right? So this is an important point to keep in mind. And so the final question is, well, what about L2 convergence, right? And so let's just calculate, and we'll show that this indeed does converge in the L2 sense as well. Right, and so what do we need to show? Well, in this case, we want to look at the integral of the difference of the square between gn and the function that we want it to converge to. Right, so does this converge in the L2 sense to 0? Right, so f is the 0 function for this example. Well, how do we make this work? Well, we look at the integral. Our domain now is between 0 and 1 of the difference between gn and f squared. Well, the function f in this example is just 0 everywhere. So this is integral between 0 and 1 of gn minus 0 squared. Of course, gn minus 0 squared is just gn squared. Right. And so, right, so what is our function? Our function is equal to 1 if x is between 1 over n squared and 1 over n, and 0 otherwise. And so this is just going to be equal to 1 on this interval, the integral of 1 on this interval, right? And so this is equal to integral from 1 over n squared to 1 over n of the function 1 squared, right? Because outside this domain, it's equal to 0, and inside this domain, it's equal to 1. And so finally, excuse me, well, of course, 1 squared is just equal to 1, so I can remove the square. And so remember, if you're integrating the function 1 on an interval, the integral is just equal to the length of that interval. So this is equal to 1 over n minus 1 over n squared. And so what we're trying to study is the limit as capital N goes to infinity of this object. Well, we just showed that this is equal to the limit as n goes to infinity of this difference. And of course, well, as capital N goes to infinity, this difference is converging to 0, right? And so the limit of this difference is indeed equal to 0, which is exactly the condition we want for L2 convergence, right? I'm sorry. We want to show that the integral of the difference converges to 0, which is the case here, right? So this is the integral of the difference, and we just calculated it's equal to this. And as n goes to infinity, these two fractions, of course, converge to 0, right? So Gn does converge to 0 in L2 sense on the interval between 0 and 1. Right? Okay, and so there's another example in the book which I would recommend reviewing yourself. Maybe I can go over it in one of the Zoom meetings. So I believe it's in section 5.4. So in the book, there will be another example of a function which converges, or a series actually of functions which converge pointwise, but do not converge uniformly, and also converge in L2, right? So it would be helpful to read this example and maybe work through some of the details yourself to more familiarize yourself with these different notions of convergence. And then if you have any questions about this example, I'd be happy to go over it in one of our meetings. Okay. Okay, and so the big thing for us is, okay, I mean, you can spend a large chunk of a semester like deep diving into all these different notions of convergence for functions and developing a theory to talk about this very rigorously. So we're not going to do that in this class. What we want to do is try to understand Fourier series, right? And so we want to now turn to convergence of Fourier series. And so the general problem, which I've written out a few times by now, I'm going to write it out in the complex case, because it turns out that, as we've seen, complex Fourier series are a little bit easier to work with than like sine and cosine. Right, so let's form our Fourier series. So say we have sum from minus n to n of some coefficient Cn e to the inx. And we want to understand, when is it the case that this series will converge as n approaches infinity to a given function f of x, right? Right, and so remember, the Cn will be our complex Fourier coefficients. So this is 1 over 2 pi integral from minus pi to pi, f of x times e to the minus inx, right? And so the general question is, well, let's suppose I define my Fourier series in this way, which we were naturally led to by considering boundary value problems with this particular coefficient. In what sense does this series converge to the given function f as n goes to infinity, right? So does it converge pointwise? Does it converge uniformly? Does it converge in the L2 sense? Does it converge in the L2 sense? And under what conditions do these various types of convergence occur, right? And so now notice that this, right, we're going to be, in this problem, we're given a fixed function, which is, for example, like the initial condition for the solution to your PDE. So it's given to you, and these coefficients depend on the function because we've calculated them in this way. And so it's going, I mean, it's going to turn out that the problem will require certain hypotheses on the function f, right? So we want to understand when the series converges. Sorry. And in what sense, right? So pointwise, uniform, L2, etc. And so this is going to require certain conditions on the function f. So there are lots of weird examples of functions where like all of the types of convergence we're talking about kind of fail dramatically. right? And oh, so I want to point out, I guess I forgot to mention this. So for this discussion, we're going to focus on Fourier series in the interval between minus pi and pi, because as you remember, all these formulas involving, right, more generally, we were looking at like minus L to L. All the formulas simplify a lot if L is equal to pi, because the L and pi terms cancel out. And it turns out that you can show that anything you prove on the interval between minus pi and pi is also true for any of these intervals, minus L to L, for arbitrary L. And so all of the theorems that we're going to do and all the proofs we do work equally well on any particular domain. I'm just choosing minus pi to pi because it's the most convenient for calculations and it's the easiest to work with. You also have a homework problem that talks about this idea. Okay, and so, right, and so we're going to begin. I mean, historically, the way mathematicians began by looking at this problem was by considering pointwise convergence. It's the most natural thing to look into first. We're going to go like sort of counter to the historical timeline, and we're going to begin by looking at what initially may appear to be the most unnatural type of convergence, but which turns out to be very deeply connected to what's going on with Fourier series. And so the first thing we're going to talk about is the L2, or the mean square convergence of Fourier series. Right? And so we're going to study and partially prove the following theorem. Unfortunately, we're not going to be able to prove this theorem in full detail, but we'll go through like the main points, and it should at least become clear what's going on. And so the theorem is the following. So the complex, well, let's suppose it's about complex Fourier series. Let's suppose we're given a function f of x. And suppose that if I integrate the square of f of absolute value of x from minus pi to pi, suppose that this is finite, right? So not the integral of the absolute value of the function, but the integral of the absolute value of the function squared. So for continuous functions, for example, if you have a continuous function, then the continuous function on this finite interval is always bounded by some number. And so this integral is always finite, right? So this includes all continuous functions, but we're allowing more general functions, which could potentially have some kind of singularity, right? So it's possible that maybe your function there's a singularity here and the function kind of blows up, but it could still be square integrable, meaning the square of it could still be integrable, even though you have some kind of thin singularity here. And so we're allowing those functions as well, in addition to continuous functions and differentiable functions and things like that, right? So maybe let me put this as a point. So singularities are possible or allowable. Let's say some singularities allowable. Right, and so under this hypothesis, it turns out that the complex Fourier series will converge to the function in the L2 sense, or in the mean square sense. So if we set Cn equals our normal Fourier coefficient, we have the Fourier series from, say, n equals minus n to n, Cn e to the inx. This will converge in L2 / mean square sense to our function. Right, and so this is, again, what's called the L2, or the mean square convergence theorem for Fourier series. And so again, what does this mean, the L2 or the mean square sense? Well, this means that if I integrate from minus pi to pi, the difference of these two things squared, that this difference squared integrated will converge to 0 as n goes to infinity. And so just as a remark, well, notice that these are these are complex numbers, right? We're allowing these coefficients to be complex. And of course, these exponentials are definitely complex numbers. And so this absolute value here is really the complex absolute value, which we introduced in a previous lecture, right? So this is like the complex absolute value. Up over here, right? Okay. Right, and so what is a good way to think about this that may connect to a more natural notion of convergence or distance or something like that that you've thought about? Well, the best way to think about this integral of the object squared is as like some kind of distance between functions. Right, so let me define some kind of notion of length, which I'll do more precisely. To distinguish from the normal absolute value, we're going to use two vertical bars. And so I'm saying that in some sense, like, so I'm measuring, like, let me define this to be like a distance between my functions. Let's say it's the distance squared. The best way to think about this is like this integral, we're thinking of it as kind of like a separation or a distance between the functions. And we want this distance to converge to 0 as n goes to infinity. Right. And so why is the square appearing here, right? So why is the square natural for distance? Well, let's just do some brief recall from working with vectors that will hopefully motivate some of what we're going to do with the Fourier series. Right, so let's say we have like, this works for any vector, any collection of vectors with arbitrary components. But let's say we have some vectors with 3 components. Say v is v1, v2, v3, and say u is u1, u2, and u3. What is the distance formula for vectors? Well, the distance is the length of their difference, right? Right. And so if I look at the distance squared, remember, what does this end up being? Well, I look at v1 minus u1 squared plus v2 minus u2 squared plus v3 minus u3 squared, right? And so this is also kind of like a mean square distance, kind of analogous to what we have up here, right? I'm looking at a difference of different values squared. The only issue with working with functions is, well, functions are defined on infinitely many points in the domain. And so it doesn't make sense to just add up a discrete number of finite points. So instead, we have to integrate the difference squared, right? And so this is very much a generalized version of distance between vectors, where we're replacing vectors by functions. And so we have to replace addition by integration because functions have infinitely many points on their domain. And so the best way to think about this is it's kind of like a convergence result for like a distance between functions, right? So the distance between the Fourier series, the partial sums of the Fourier series for fixed n, as n goes to infinity, this function gets closer and closer to our fixed function f in this sense, right? So this is a good analogy to keep in mind. And as we mentioned in an earlier lecture, like what we're doing here is really kind of like an infinite dimensional version of linear algebra, where vectors are replaced by functions. And a lot of the important concepts will transfer over. Right. And so another thing I wanted to point out is to remind you, well, the distance, right? This is the length of the difference between the two vectors, right? And so what was the length formula? Well, the length squared is just what we have here with just the components of v, right? It's v1 squared plus v2 squared plus v3 squared. But remember, you can write the length in terms of the dot product, right? So this is the same thing as if I take the dot product of v with itself, right? Where this is the usual dot product. And so this gives you a correspondence between lengths of vectors and the dot product, and in particular allows you to relate any calculations involving lengths of vectors to the dot product. And remember that the dot product is also a key tool for analyzing orthogonality or vectors being perpendicular. And so this notion of orthogonality is kind of embedded here, and in particular explains why it's natural to have squares when you're calculating distance, right? I mean, it's basically reduces to the Pythagorean theorem, right? And so what we're going to do is, in fact, I mean, we've already done this partially, but we're going to go into a little bit more detail. We're going to introduce a notion of the dot product for functions, and this is going to allow us to more carefully work with this difference here, this difference, the square difference, and we're going to use this to understand this notion of distance more precisely, and this will allow us to prove the convergence result. And so everything we're about to do, I think it's a helpful exercise to try to think back to just working with like distance between vectors and trying to like interpret it in terms of distance between functions instead. Okay, and so let's turn to doing that. There's one thing I just want to quickly review related to complex numbers, which I didn't have a chance to talk about in the previous lecture. And then we'll move forward with what I just outlined. And so this is the notion of complex conjugates. You'll see why this is relevant shortly. So let's suppose I have some complex number z, which is equal to a plus ib. Right, so some complex number. The conjugate is defined to be, usually we write a bar over z. And so what you do is you keep the real part a the same, and for the imaginary part, you just flip the sign, right? So b could be a positive or negative real number. For the complex conjugate, you just flip that sign, right? And so this is usually called like z bar is the way we would pronounce this, or the conjugate. And so notice that, well, this notion of conjugation is related to lengths of complex numbers in the following way. So let's say I multiply my number z by z bar, right? So this is equal to a plus ib times a minus ib, right? And so if I multiply this out, well, I get a squared minus IBA plus IBA, these terms will cancel. And then I'm finally left with minus I squared B squared. Well, I squared is -1. So if I take the negative of that, I get +1. So this is A squared plus B squared, right? Since I squared is -1. But A squared plus B squared is just the length of my complex number squared, right? And so then we have the following useful formula, which relates complex conjugates to length, right? And so this is going to show up later. So I just remembered that I had not gone over this in the review of complex numbers. So I just wanted to bring this into play quickly here. Okay. And so now what we're going to do is, again, go back to analyzing this integral and try to understand it as like a distance between functions in this way. And in particular, what we're going to do now is introduce a notion of dot product for functions. Great. Okay, and so this is something that's called an inner product, right? And so what we're going to do first is look at the inner product on the interval between minus pi and pi, which is where we're focusing on for this theorem. Right, so let's suppose that f and g are two functions on the interval minus pi to pi. Right, so the inner product of f and g is defined to be, well, we write f comma g in parentheses, and this is equal to 1 over 2 pi integral from minus pi to pi of f of x times the conjugate of g, complex conjugate dx. Right, and so we're allowing our functions to take complex values. Right, so why are we allowing our functions to take complex values? Well, we're working with Fourier series here, and in particular, our Fourier series could potentially be complex valued, right? These could be complex numbers. It doesn't matter that x is a real number. E to the in x times the Fourier coefficient could be complex. And so, well, it turns out we're going to analyze this difference squared in terms of this inner product, and so we need to allow our functions to be complex valued. Right, and so, so this is the inner product of two functions. And so note, well, what happens if I take the inner product of a function with itself? Right, let's say I take inner product of f with f. Well, this is 1 over 2 pi integral from minus pi to pi of f of x times the conjugate of f, right? But remember, if it doesn't matter which x we pick, remember if you take the conjugate times the conjugate of a number times itself, it's always the absolute value squared, right? So it's always the length squared. So this is equal to 1 over 2 pi integral from minus pi to pi of absolute value of f, or complex length of f squared, right? And so this is defined to be like the absolute value of or not absolute value, sort of like the length of or the size of the function. Right, so this is the what's called the L2 norm, which is like the length or the size of a function. Right, and so what this shows us is, well, we can describe this length in terms of this inner product, which we just introduced. And so what you should have in mind here is, well, this is a lot like the length squared of a vector, right? So let's go back to this picture we had before, right? The length squared of a vector, you can encapsulate using the dot product by taking the dot product of the vector with itself. And so that's exactly what we have here, except for functions instead of vectors, right? So this is like a dot product of functions. And so this is like your length, or the length squared is given by the dot product of v with itself, right, for a vector. But now we're replacing the vectors by functions. Right, actually, this is the L2 norm squared, right? Right, so what does this mean? This means that the L2 norm is the square root of what I have above, right? Right. Okay, and so I want to go through two quick examples to help us understand these dot products a little bit better. The first is just let's return to the theorem we're trying to prove, which is this L2 convergence theorem, and interpret it in terms of the inner product, or the norm, the L2 norm that we just introduced. Right, so we're trying to show that if I look at integral from minus pi to pi of the difference between our Fourier series at point n and our function f, that this converges to 0 as n goes to infinity. Let's interpret this in terms of these dot products. Right? So let's define, say, e sub n is equal to e to the I n x, right? Just to simplify the notation a little bit. Well, if I look at this, what is this? This is integral from minus pi to pi, length, or sorry, not length, absolute value of the difference between the series. So let me write the Cn En minus f. Right. So this is exactly what we call the L2 norm of the difference of the two functions, but it's squared and, like, say, multiplied by 2 pi, right? And so this is equal to 2 pi times this L2 norm of the difference. But squared, right? And so all I've done is just, right, using this definition we have here, what is this thing squared equal to? It's just equal to the integral of the function squared times 1 over 2 pi, right? It's just equal to this quantity. This is exactly what we called the L2 norm squared. And so the integral of the difference of these two objects squared can be rewritten in this sense, right? And so we want to show that the limit right, I want this converging to 0 as n goes to infinity, right? And so again, if we think of this like a distance between functions, we're trying to show that this distance is converging to 0 as n goes to infinity, right? Right, and so using this new notation, we can rephrase the theorem, the L2 convergence theorem, in the following way. So if your function is, the integral of the function squared is finite, this is equivalent to this quantity here, which we call the L2 norm being finite. And so the theorem says that if this norm is finite, then in this sense, this distance will converge to 0 as n goes to infinity, right? So your Fourier series will approach f in terms of this measurement of distance, right? And so this is like a special measurement of distance between functions, right? And so maybe one more quick example which relates this to Fourier series. And so what I want to illustrate in this example is the connection between inner products and orthogonality for Fourier series. And so the first thing to point out is, well, right, I just want to do one quick calculation and then we'll get to the point. And so notice that, well, what are the important objects for Fourier series? They're these complex exponential terms. And so if I look at e to the I nx, if we use the Euler formula, remember this is the same thing as cosine nx plus I sine nx. Well, what happens if I take the complex conjugate of this number, right? Why am I interested in complex conjugates? Well, because they show up in the definition of the inner product, right? And so if we're doing anything involving this inner product or this L2 norm, we need to understand what the complex conjugate of our exponentials are if we're going to say anything meaningful about Fourier series. Well, by definition, this is equal to cosine of nx minus I sine of nx. But remember, sine is an odd function, cosine is an even function. And so this is equal to, well, cosine of nx is the same thing as cosine of minus nx. And on the other hand, I can, since sine is odd, I can bring the minus sign inside. So this is cosine minus nx plus I sine of minus nx. But then using the Euler formula again, this is just equal to e to the minus inx, right? And so what this shows is that the complex conjugate of this exponential is just e to the minus inx, right? Or if I use the notation from before where I'm letting the shorthand e sub n is e to the inx, this says that complex conjugate of en is e minus n, right? So taking the complex conjugate flips n to minus n when working with these exponentials. And so what I'm going to do now is return to some of these orthogonality principles we have between these complex exponentials and just write everything in terms of the inner product, right? So from before, we know that if I look at the integral from 1 over 2 pi minus pi to pi of e to the inx times e to the minus imx dx, for n and m are just arbitrary integers, that this is equal to 1 only when n is equal to m and 0 otherwise, right? And so this was just our orthogonality principle for the exponential sums, which plays a key role in understanding what the Fourier coefficients have to be, et cetera. But now I'm going to rewrite this using what we just observed. So this says that if I look at integral from minus pi to pi, 1 over 2 pi times that, and I look at e to the inx times the complex conjugate of e to the imx dx, that this is equal to 1 if n is equal to m and 0 otherwise. But this here is our inner product of these two functions, right? And so this gives us the following result, which I'll phrase as a proposition, right? And so this is the orthogonality. So let me define e sub n is e to the inx as before. Well, this above here is just the inner product of en and em, right? And so the proposition is that e sub n inner product with e sub m, where these are the complex exponentials, is equal to 1 if n is equal to m and 0 otherwise, right? And so you want to think about this inner product as like a dot product. And so this should remind you of like orthogonal vectors and the dot product, right? So, or orthonormal vectors and the dot product, right? So think, right? And so why am I saying this? Well, recall that if I take the dot product of two vectors, when is this equal to 0? Well, this is equal to 0 if and only if they're perpendicular. Right, and perpendicular is just another way of saying orthogonal is just another way of saying perpendicular, right? And so this orthogonality principle, when interpreted in terms of our inner product, is kind of like a natural generalized version of this principle from linear algebra or from multivariable calculus, which is the dot product detects when things are perpendicular. So this inner product now detects when functions are orthogonal. And so since orthogonality plays such a key role in understanding Fourier series, we're going to see, we kind of see that here. And this is why it turns out that the L2 convergence is a natural type of convergence to work with. It's really like the role of orthogonality in understanding Fourier series, and then the importance of the inner product in understanding the connection of the inner product to the distance that we're working with in L2 convergence, which makes this kind of natural, even though it may not appear so initially. Right. And so let me just quickly follow up this proposition then with a definition, which is nothing new other than just kind of a little bit more terminology. Right. So suppose f and g are two functions, say on the interval between minus pi and pi. Then f and g are orthogonal if their inner product is 0. Right, so if the inner product of f and g is 0, again, this is just a direct generalization of the notion of vectors being orthogonal. Right, so two vectors are called orthogonal if their dot product is 0. For us, two functions are orthogonal if their inner product is equal to 0. Right, and so again, this is kind of like the functions being perpendicular, or not literally perpendicular, but it's like an analogy or like a generalized version of perpendicular. Right. And so finally, let's kind of summarize everything we've done up until this point. So we're looking at this object, which is the complex Fourier series. Which I can write as sum n equals minus n to n, Cn using this notation, say E sub n. Right. And so, well, what was our Fourier coefficient here? This is 1 over 2 pi integral minus pi to pi of f of x times e to the minus in x dx. But I can now write this as integral from 1 over 2 pi, integral 1 over 2 pi times minus pi to pi, f of x times the complex conjugate of e to the inx using what we observed above. But now this is just the inner product of my function with en, right? And so I can rewrite my Fourier series now as sum from n equals minus n to n of, well, Cn is just equal to this inner product, right? Times En, right? And so we will, what are we going to do now? We will study the following theorem. So this is called the L2 convergence theorem. Which is the theorem I introduced at the beginning of the lecture, just rewritten in terms of the new notation, right? So suppose we know that the L2 norm of our function is finite, right? So remember, this is 1 over 2 pi integral from minus pi to pi of absolute value of f squared, right? So the conclusion is that if I look at the L2 distance, meaning the length of the difference of my Fourier series and my function, Fourier series stopped at point n, that this distance will go to 0. And remember, well, let me plug in this formula for the coefficients. Right. And so again, this is the L2 distance. Right, so the L2 convergence theorem, or the mean square convergence theorem, says if my function is, the integral of my function squared is finite, meaning this L2 norm is finite, then if I look at the length or the L2 norm of the difference between my function and this partial sum of my Fourier series with the coefficients given by this formula, then this difference goes to 0 as n goes to infinity, right? And so this is like saying the distance between these two functions decreases. And so eventually if the distance goes to 0, that means they have to be the same thing in the limit, right? And so this is the sense in which Fourier series will converge to a function that has the L2 norm being finite. And so remember, this allows for a wide class of functions. For example, your function could have like 100 different singularities between minus pi and pi. It could be blowing up at all sorts of different points. And the Fourier series will still converge in this sense, even if your function is kind of like a bizarre or rough looking function. This is not going to be the case for pointwise or uniform convergence when we turn to that in a lecture or two. Okay, and so now what we're going to begin doing, this is kind of like has been a lot of possibly repetitive. I apologize if this lecture has been a little bit repetitive since I'm saying the same things over and over again. We're going to start trying to understand how to prove this theorem. And so it's going to turn out that at a certain point in the argument, we're not going to be able to proceed because we're going to have to use a result that you would learn in like a more advanced class, for example. But I'll at least indicate what is done to prove the theorem. And so this is not just kind of like a pedantic, like academic exercise. So it's going to turn out that a lot of the tools that we use to set up the proof will be useful for working with Fourier series. And so in particular, some of the stuff we're going to prove, completely prove, we're going to use later on when we talk about pointwise convergence of Fourier series, right? Right. So let me just, I guess I'll title this like beginning the proof. Right. And so, I mean, the key takeaway is we're going to be using orthogonality all over the place. And so what I want to do to motivate some of the calculations we're going to do soon is, let's again go back to our analogy with vectors. So I want to just recall Pythagorean theorem, but the version of the Pythagorean theorem for vectors. Right. And so the theorem is the following. So let's say I have two vectors which are perpendicular. Let me not draw it like this. Say this is my vector u, this is my vector v. They're perpendicular. This means that the dot product of u and v is 0. Right. So this is not the Pythagorean theorem. I'm just reminding you about this principle. So the Pythagorean theorem says that if you have two vectors which are perpendicular, then if I look at the length of v plus u squared, that this length can be calculated by looking at length of v squared plus length of u squared, right? And so this has the interpretation which is related to the more familiar Pythagorean theorem, maybe from geometry. Well, let's say this is the origin over here. Well, then this distance here is just the length of u, and this distance here is the length of v. And so, of course, the length of u squared plus the length of v squared should be equal to this length here, right? That's the more familiar Pythagorean theorem. And so you can see that L, if you do some basic vector geometry, you can see that L is equal to v plus u, right? So this is equal to, right, the vector v plus u will just be equal to that. Well, yeah, I mean, I haven't given you the orientation, right? So maybe it's better to, it may be v minus u, you would have to check, but this is, it's definitely the length squared is equal to this length. Right, so that's the connection to the more familiar theorem, maybe from geometry, but you can actually prove this just using dot products, right? And so, right, how does the argument proceed? Well, remember that if I look at, if I look at the length of my vector squared, I can recast this in terms of the dot product, right? So this is the same thing as v plus u dot product with itself, or shoot, sorry, plus, right? Right, this is again the connection between dot products and lengths of vectors. But now remember, we can distribute dot products like we would distribute multiplication with addition, right? Because we have some kind of linearity property for dot products. And so this brings into play orthogonality, right? And in particular, if you have orthogonal vectors and you're calculating lengths of like combinations of these vectors in some way, orthogonality is always going to be helpful because lots of dot products will cancel out and they'll just become 0. And so in particular here, well, if I distribute, this is equal to dot product of v with v plus dot product of v with u plus dot product of u with v, and then finally plus the dot product of u with itself, right? But because these vectors are orthogonal, right, so each of these terms is 0, they're perpendicular, and so you're just left with v dot product itself, which is the same thing as the length of v squared, and then also the length of u squared, right? So that's the proof of Pythagorean theorem for vectors. What we're going to do now is the same thing, but for functions, right? And so what I want to prove now is the Pythagorean theorem. For functions. And so the theorem is the following. Suppose that I take the I have two functions and their inner product is 0, right? So f and g are orthogonal. The conclusion is that if I look at the L2 norm of f plus g squared, this is equal to the L2 norm of f squared plus the L2 norm of g squared. And similarly, if I look at the L2 norm of the difference, this is equal to the same thing. Right. And again, the key point is you really need them to be orthogonal for this to work. Right. Okay, and so how do you prove this? Well, the proof, it's really going to be formally the same argument we did up here, but we just have to interpret everything carefully in terms of like the definition of the inner product, right? So let's do this argument carefully. I'm just going to prove the first one. The proof of the second identity is the same, or you can similarly just replace g by minus g in the argument, right? And you get the same thing. Right, so the proof is, well, recall that using, what was the first step we did for vectors? We replaced the length or the norm, which is this thing here. We replace this by the inner product, right? Because whenever you see that things are orthogonal, to take advantage of that, you want to bring inner products into play. So the length of f plus g squared is the same thing as taking the inner product of f plus g with itself, right? Right. And so by definition, what is this equal to? Let me just continue below here. So this is equal to integral, or 1 over 2 pi times integral from minus pi to pi of f of x plus g of x times the conjugate of the same thing, complex conjugate. Right. And so, right, well, we have the following fact, which I guess I forgot to review earlier, which is if you look at, say, z plus w, and you take the complex conjugate, this is equal to conjugate of z plus conjugate of w. This is easy to check. So maybe you should pause the lecture and just verify this for yourself as a good exercise. And if you're confused about this point, of course, you can ask me and I'll go over it. But it would be helpful maybe just as a little exercise to just check that. Now it should only take like 1 minute. Right, and so if I use this property here, we see that the L2 distance or length, sorry, the L2 length of f plus g is equal to 1 over 2 pi times integral minus pi to pi f of x plus g of x times conjugate of f plus conjugate of g dx. And so now I'm just going to distribute everything, right? I'm just multiplying a bunch of functions. So let's like write this all out. So this is 1 over 2 pi integral from minus pi to pi. Well, I have f of x times f bar of x plus f of x times g bar of x, right? Plus now g of x times f bar of x. and then finally plus g of x times g bar of x dx. And so I'm going to break up these integrals into different terms, right? So this is 1 over 2 pi. Well, I have the first thing. Well, notice this is just the absolute value of f squared, right? Because of the fact that z bar is equal to absolute value of z squared. And similarly, this is the absolute value of g squared, right? So I have these two terms, absolute value f of x squared dx. And let me bring the other term g over in the front. So integral from minus pi to pi, 1 over 2 pi times absolute value of g of x squared. And then I have the two remaining terms. So my first term is integral from minus pi to pi of f of x times conjugate of g dx. And then finally, 1 over 2 pi times integral from minus pi to pi of g of x times f bar of x. Right. And so now let me write this in terms of inner products, right? So the first two quantities are, well, this is just the L2 norm of f. Right, so this is L2 norm of f squared. This is L2 norm of g squared. And this is, well, notice this is our inner product of f and g, right? And so the first three terms are equal to norm of f squared plus norm of g squared, and then plus the inner product of f with itself. But by hypothesis, these functions are orthogonal. And so in particular, we're assuming that this is 0, right? And so this is just going to be 0. And so finally, I just have to understand, well, what is going on here? And so, I mean, there's technically something that we need to prove here. I'm going to maybe wave my hand over the details a little bit, but I just want to point out that right, so I need another fact, which you can check. Right, so let's say I look at now a product of two complex numbers, and I take the complex conjugate of the product, that this is equal to complex conjugate of the first number times complex conjugate of the second number. Right, so maybe you should check this yourself. And so in particular, what happens if I have like some number z times the complex conjugate of w, and let's say I take the complex conjugate of that product, well, this is equal to z bar times now the conjugate of the conjugate, right? But remember that complex conjugation flips the sign of the imaginary part, right? So w bar, the imaginary part, has the opposite sign as w, but if I take the conjugate again, this is the same thing as just going back to where I started, right? So this is equal to z bar times w, right? And so, well, why am I going through this? Well, that's exactly what we have here, right? So I have g times f bar. This is the same thing as the conjugate of using this logic of f times g bar, right? And so this is fact one. Fact two is that you can take complex conjugates out of integrals, right? So if I look at the integral of complex conjugate of some function h of x dx, this is the same thing as the complex conjugate of the integral. This is maybe a little bit harder to prove. What you would basically do is break up the function h according to its real values and its imaginary values and see what happens with the conjugation. Maybe I'll give you a homework exercise which outlines how to check this. Right. And well, if I use this fact here, this implies that well, I'm looking at the integral of g times f bar, which we just showed is the integral of the conjugate of f times g bar. And then if I can take the conjugate outside the integral, right, this is equal to now the conjugate of the inner product, right? So this is equal to FG conjugate. And so the final term we have here is the complex conjugate of the inner product. Right. But the complex conjugate of 0 is also 0, right? So this is 0 bar, which is 0. And so these two excess terms vanish, both of them, right? And so at the end of the day, we just end up with norm of f squared plus norm of g squared as desired. Right, and remember we started with norm of f plus g squared, right? And so this is the proof. So if you go through similar calculations in the book does something which I think is kind of a unfortunate choice, which is they assume all their functions are real valued. If all your functions are real valued, the proof of this is a little bit easier because you don't have to worry about complex conjugates. Because, well, one thing you can check pretty easily is that if you have a real number with no imaginary part, then complex conjugation doesn't do anything, right? And this is just because complex conjugation only acts on the imaginary part. So if the imaginary part is 0, it won't do anything. And so then in that case, well, you don't have to use all this stuff in blue. You just get inner product of FG with itself 2 times. And so both of those terms are then obviously 0. If you're working with complex valued functions, you have to just worry about some of these extra technical facts related to the complex conjugate. And so why are we going through all this extra pain to deal with complex valued functions? Well, remember, I mean, in applications, most people when working with Fourier series will work with complex Fourier series because they're easier to work with. And so we want to make sure that we're allowing everything to be complex valued. It's just a little bit of extra pain, but it has better payoff in the long run if you do it this way, I think. Right, and so that's the proof of the Pythagorean theorem for functions.